I can fight monsters, I can't fight physics.
Hello, so Em sent me a few more last minute questions for your paper 2 AQA. So let's have a look at this one. So in 2012, a skydiver jumped from a helium balloon. So as soon as you see the word skydiver, think terminal velocity. So that's probably the question. From a helium balloon 39,000 meters above the Earth's surface, skydiver reached a maximum speed. So that means terminal velocity. Maximum speed of 377 meters per second. So jumping from 39,000 meters allows a skydiver to reach a much higher speed than a skydiver jumping from 4,000 meters. So the question is, explain why. So first of all, as soon as you see terminal velocity, you got to think terminal velocity. You got to think, especially for a skydiver, weight equals drag. Okay, so the weight is acting downwards. So if you used to draw it, so this is the skydiver. You've got the weight downwards and you've got the drag upwards. Okay, and they should be balanced. All right. The key thing here, drag increases as speed increases. So make sure you put that as an explanation, but that's not what this question is about. Okay, so typically if you jump from 4,000 meters, you'll reach about 120 miles per hour, which is about 60 meters per second. So for some reason, if you're at a higher altitude, you're reaching a higher maximum speed. That means your weight is clearly the same. Drag is not building up. So why is drag not building up? Well, what is drag? Drag is air resistance. Okay, and what do we know? Now, this actually, it looks like a chapter 10 or chapter 9 or 10 question about terminal velocity. It's actually chapter 11 question about pressure. So if you remember, how does pressure increase with or change with altitude? Well, the higher up you go, the lower the pressure. So as altitude increases, pressure decreases. Why? Because the air is thinner, there's less air particles or there's less weight of particles above you. Okay, and that's what this question is asking. So clearly, if there's less pressure, there's less air particles. If there's less air particles, there's less drag. And if there's less drag, that means you need to go faster here to build up more drag to equal the weight. That's why it takes longer. And therefore, if it takes longer for the weight to equal the drag, therefore you're still accelerating at that time. So let's put that into words. So at 39,000 meters, so we'll start off with basics. The air is thinner. So we'll start off with saying what we know. So we'll start off with what you can say. All right, state the obvious stuff. It might not be the answer yet, but you'd be surprised how much the obvious stuff is the answer. It's just the last bit is linking it all together. Air is thinner. Okay, so what does that mean? That means less particles. And what does that mean? That means less drag or less air resistance, they prefer, but I always go to drag straight away. You shouldn't deduct a mark for that. That should be the answer. So there's less drag. If there's less drag, then therefore it takes longer for drag to equal weight. So that means you are accelerating for longer because you haven't reached your max speed yet. Accelerating for longer. So that means you're going to a higher maximum speed. So that's one way they could ask you about the what ifs about terminal velocity. The other one, if you remember, I talked about, well, what if you were on Earth and you dropped things? So if I had a VT graph and I said to you, well, this is a parachutist, this is your classic TV graph, and you reach terminal velocity there. What would happen if you was something lighter? Well, if you were lighter, look at this bit here. This is the important bit. If you're lighter, you got less weight. If you got less weight, you need less drag. Then, therefore, you'd reach that drag value much earlier, and therefore you wouldn't have been accelerating for longer. So it would look like this. So there's a terminal velocity there. And if you was heavier, Now look at the formula again. Let's assume you dropped from the same altitude, 4,000 meters, or even 39,000. Doesn't matter which one we use as a constant. If you were a bigger weight, that means you need more drag. Therefore, you need bigger speed. That means you need to accelerate for longer. So therefore, it would look like this. So there's your TV. So things that are heavier have a higher terminal velocity and it takes longer to get to it. Things that are lighter have a lower terminal velocity and it takes much earlier to get to it. So when you drop a book and a piece of paper from the same height, you'll notice the paper takes forever to get to the floor, whereas the book is slammed to the floor because the paper has reached its terminal velocity earlier, so it's not accelerating anymore. Okay, so that's this question about terminal velocity. So they could ask you about how pressure or altitude, changes the drag and the effect of that, which is what this question is. And they could ask you the opposite. So I remember a question a while ago. They asked on Mars has a much denser atmosphere. I think it was Mars or some other planet. It doesn't really matter what the planet is. It says much denser atmosphere. So you think denser atmosphere, okay, so the air's thicker, more particles, more air particles, the drag builds quicker. So that means the drag will build quicker, therefore your terminal velocity will be smaller because the drag would have equaled the weight at a much earlier time. Okay, so those are the sort of variations. Expect a terminal velocity question because it hasn't come up yet. So next question looks like as soon as you see a pivot, okay, I'm thinking moments. All right, so what have we got? Let's read the question. When the ramp is lowered, work is done to stretch a spring on the side of the ramp. Elastic potential energy. So as soon as you see elastic potential energy is equal to a half KE squared. So that's on your formula sheet anyway, so you don't have to worry about that. But as soon as you see buzzwords, you got to think what formulas do have to spring to mind. So this thing is being balanced and it's a moments question. So that must mean the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Okay, so this is your go-to. So straight away, I've just read the first two sentences and I've plucked two formulas out. And we also know moments is equal to force times perpendicular distance from the pivot, and both of these are right angles to the pivot, so we haven't got any issues. There's no angles here, there's no 20 degrees, 30 degrees, so we don't have to worry about that. Plus, don't expect it anyway on a GCSE paper. So with the ramp horizontal, the moment caused by the weight of the ramp is, so this moment here, which is clearly your what's that, the anti-clockwise moments. Okay, that is 924. So now there must be a clockwise moment, and that's clearly from this force here. The force is upwards, so this is creating a clockwise moment. Okay, so calculate the elastic potential energy. So in order to do that, we need E equals a half KE squared. Okay, we've got the E. Okay, and that's in the correct unit, so that's good. We need the K. So now you got to ask, well, where can I work out K? Well, you've got a spring. And springs, chapter, I think it's either 10 or 11, is Hooke's law. So F equals KE. All right, so maybe we could work out the force, which we should be able to, because if you look at this formula here, sum of the clockwise moments is equal to the sum of the anti-clockwise moments. So we've got the anti-clockwise moments, which is 924 Newton meters, so that's fine. And for the clockwise, we don't know the force, but we know the distance, and that was in meters, by the way. That was 0.15 meters. So now we could work out the force. So all we've got to do, we need to get F on its own. So F times 0.15. So we need to take the 0.15 to the side. So do the opposite of multiplying. So F is equal to 924 over 0.15. Okay, so if I put that in, I can work out F. So F, now this is 6 marks, so it's not just rearranging, it's not just using two formulas, it's actually, we're going to use a few formulas here. So I'm just showing you the basics of a way. You can find other ways of doing it, depends how your brain thinks, but if not, these are the sort of buzz things must be going in your head. As soon as you see keywords, key formulas should be coming up. So this is 6160 newtons. Now, I've got to work out K. So in order to work out K, I've got F equals KE. So if I use F is equal to KE, well, this 6160 is equal to K, and it's caused an extension of 0.25. Okay, so I can put that in. I can work out k again. To get k on its own is times by 0.25, so you divide it to get to the other side. So 6160 over 0.25. So it's the same as times it by 4. So answer divided by 0.25 is equal to, so that gives me k, I'll put it here, so k is 24640. And then once I've done that, well, I can just work out the energy here. So it's a half times 24640 times 0.25 squared. So if I do that times by 0.5 times by 0.25 squared equals, so I get 770 joules. Now, there is another way to do this. There is another formula for elastic potential energy. E is equal to a half Fe. Now, this is not on the GCSE AQA spec, so there's no one really should be going to that, because you can work out F using the moments thing you did here, and then you can just put it directly into that. But you're not expected to know that. Right? You know, this formula is not on the spec. It's an A-level formula, although you could actually derive it if you had to, but it's not there. So I'm expecting for 6 marks, they're expecting you to do all of this. Okay, so that's a nice question because there's a lot of calculations, but all of these formulas should be springing to your mind, pardon the pun, because you're looking at keywords: elastic potential energy, oh, stretch spring, F equals KE, oh, pivot moments. Okay, so that's the sort of mindset you got to do. Or worst case scenario, you see some numbers, know the symbols for them. So spring stretched, E, okay, E equals half KE. I can use that. Half KE squared, sorry. I can use that. F equals KE, I can use that. Do you see my point? So just what formulas can I use with the quantities given? And sometimes that will get you a lot of the marks anyway, and maybe something will click by then. Okay, next question. Now, this hasn't come up didn't come up last year. Okay, so I'm expecting it this year. So we didn't see momentum last year. So conservation of momentum before, momentum after. Okay, so don't forget momentum was MV. You're probably thinking, why am I writing that here? Because it's got nothing to do with momentum. Watch what I do. So you've got a question and you've wrote out everything here, which is great. You've got force and time. Now, 180 milliseconds is 180 times 10 to the minus 3 seconds. Okay, so don't forget your prefixes, a good way to sort of test if you know everything. So child of mass, so you got the mass, yeah. When the child reached the ground, she took 180 milliseconds. During this time, so she slowed down and stopped. So the final velocity is 0. So calculate the velocity of the child when she first touched the ground. So they're actually asking for you. So what formula do you know? First of all, with F and T, and there's only one. Okay, you've got all your, you've got F equals ma, which is great because that could be your starting point, but you don't actually have to go to that. I mean, I'll just show you anyway. Well, A is V minus U over T. So F is equal to MV minus U over T, which is equal to F is equal to MV minus MU over T. Okay, so therefore, now you're probably thinking, oh, do I need to derive all that? No, because F equals MV minus MU over T is given. So you should be able to go straight to that. Another way of writing this is MV minus MU is equal to change in momentum. So F is equal to change in momentum over time. Okay, and that's a good one to sort of remember because we actually use that for the explanations as to why things reduce the force by increasing the impact time for the same change in momentum. Okay, so let's have a look how do we use this formula. So I'll start off with the change in momentum one. Well, we've got to work out, so you got F here. So if I write this formula, F is equal to change in momentum over time. So you got 800 newtons is equal to change in momentum over 180 times 10 to the minus 3. So we can work out delta P, or change in momentum, is equal to 800 times 180 times 10 to the minus 3. So that gives you 144. And change in momentum is mass times velocity, so that's kilograms meters per second. Now, the question is, it's asking for the velocity. Okay, so they're giving you the mass. Now, the question is, that's the change in momentum. So the final momentum was 0 because you've hit the ground. So what is the initial momentum? Well, it's 144. Okay, because that's what it's changed by. It's 144 to 0. So that must mean that is now equal to mv. So we can now work out v because it's just 144 over the mass, which is 32. So if I just do that on the calculator, divided by 32, so that gives me 4.5 meters per second. So the key thing here is when you work out the change in momentum, you've worked out what it was before and what it's gone down to. Well, it's gone down to 0 because it's stopped. So therefore, the initial momentum must have been 144. So from that, I've worked out the initial velocity u. Okay, so I'll put v there. I should have put u. Now, the other thing that hasn't come up, they haven't asked the question yet. Looking at this formula here, they haven't asked things like how does certain safety features reduce the impact force. So usually, like on a car, you've got the seat belts stretching, you've got the side impact bars or crumple zones crumpling, and you've got the airbags inflating, deflating. So that is the context. And then the three other marks are increases time of contact, reduces the force for the same change in momentum, for the same delta P. You have to write that down for the fourth mark or the third mark if it's a 3 marker, because when you're seeing the relationship between time and force, you have to also say what was constant. Okay, so if you're measuring the relation between two variables, the other one has to be your constant or your control. So look out for explanation questions like that. Right, ray diagrams. This hasn't come up for 3 years. In fact, if you actually got some time, everybody, and you go to the 2021 paper. Okay, I think it was November 2021. Okay, a lot of the stuff that hasn't come up for the last 3 years has come up on that paper. So there's a sort of a premonition or a prediction, whichever you want to call it. But it'll be good preparation anyway, because it goes through all the stuff that we've gone through today, or I'm going through today. So lenses can be used to form an object. Complete the ray diagram figure 2 to show a convex lens forms the image of the object. Use an arrow to represent the image. So we know it's a convex lens because look at the arrows here. Okay, so arrows are up. If it was a concave lens, the arrows would be down. Or sorry, the other way. Okay, and I'll come to a concave example later because that's the other sort of spanner in the works I can give you. So what you do, they've done one of them. They've done one of the rays. If I was being totally strict, yeah, I think the arrows are shown. I'll always make sure you draw the arrows for each line. They've missed out one. You've got to draw 2 rays. The one they've drawn is parallel, then goes through the focal length. The other one is from the top of the object straight through the center. So I'm going to draw that one with my ruler. That's really good. Okay, and again, what have I forgotten? I've forgotten the arrow. And then what you do, where they join up, use a ruler again. My ruler's too big to put on the screen this way. So there's my, oops, sorry, it's no good, is it? That is good, yeah. Yeah, that's fine. And then draw an arrow to show this is, and just write down this is the image. And then the next bit of the question they're going to ask you, describe the image. So first of all, it's inverted. Second of all, it's real. How do you know it's real? Because it's on the opposite side of the lens to the object. Okay. And the third one, look at the size of it. The arrow, the size of the image, it's diminished. And then what you can do, work out the magnification. So the magnification is the image height over the object. So this time it's going to be an answer less than 1 because it's diminished, or it's a not a magnification in this case. If the answer was, if your image was larger than the object in terms of the length you measure a ruler, and the magnification will be bigger than 1. Okay, so that is that's too easy. Okay, I'm pretty sure. Actually, this was a higher question, so I'm pretty sure it must be a higher question. Otherwise, you wouldn't be giving it to me. So let's look at what they should be giving you. They should be giving you a question. I'm going to change this now. They should have given it to you. If they want to make it hard, they should have put the object here. So I'm just going to call it O. Now, what would you do if the object's here? So the first, these 2 rays are correct. I'm just going to go over the lines just to show that what you be expected to draw. So you expected to draw that bit and that bit. Take your time in the exam. Don't rush it like me. So that's the first one. It goes parallel, then it goes with focal length, and then the other one, it goes from the top of the object straight through, and it'll look like that. And as you know, it looks like they're diverging. So they're certainly not going to come to focus on the other side of the lens. So what you have to do, you have to draw dotted lines. And they have to be dotted because these are imaginary, or they're not there. Okay, so extend them backwards, and there you go. And here is your image. So Draw a line, nice and big. Draw an arrow. Right, so I'm going to put this as I. Now, what can you tell me this time about the image? First of all, it's virtual because the object and the image are on the same side. So this is virtual. It's upright. And it is magnified, clearly, because it's larger than the object image. And again, work at the magnification. That's the only maths there is to this. And just a bit more practice, let's just do a concave lens, okay, or diverging. So here's the visitor. Now, can you look at the arrows on top of the lens, okay, or the pointers, I guess. So what do we do here? Again, one goes through the center from the top of the object, so I'll do that first. Okay, let me do that again. There you go. Okay, draw your arrow, show the direction. And then this one, what you do, you draw the parallel ray first. Okay, but this time it's not going to converge at the focal length here. It's not going to do this. All right, it's not expected to do that. So what you have to do, you have to draw a dotted line from this focal length to that point there. Okay, and then go outwards. So now on the left hand side of the lens, you draw it dotted because it's imaginary, and then you extend out. Okay, now the question is, where is the image? It's where the two lines intersect. It's here. And again, what can you tell me about the image? It's upright. It's virtual. Okay, because it's on the same side as the this is the object, by the way, and this one is diminished, isn't it? And again, I can work it out this time, can't I? So this is two big boxes. This is 0. Let's see, 0.2, 0.4, 0.5. So the magnification here is 0.5 over 2. So just put it in your calculator. But you should be able to do that in your head, even though I'm using a calculator. That's 0.25. So it's clearly smaller. Okay, so those are the three different types I could ask you to do. So just keep practicing. Move the object around yourself. For a cave one, the object will always be outside the focal length and never be inside it. Okay, so practice those. Now let's move on to what they haven't asked also for a very long time, which is filters. Okay, first of all, make sure you know why you see. Let's say, for example, you got a blue object. Why is a blue object blue? Because it absorbs all the 7 colors of the rainbow: red, orange, yellow, green, blue, indigo, violet, or RGB, and it reflects blue. Okay, so if I said to you, why does an object look red? It's absorbed all 7 colors of the rainbow and it's reflected the red. If I said to you, why does something look green? It's absorbed all the colors of the rainbow from a light bulb or from the sun, and it's reflected the green. Why does something look white? Because that's what they could ask. Well, it's absorbed all the 7 colors of the rainbow, or the spectrum, sorry, I shouldn't say rainbow, and it's reflected all 7 colors of the spectrum. Okay, and why does something look black? It's absorbed all the 7 colors of the spectrum and it's reflected none. Okay, so darkness or black is the absence of light, isn't it? So that's why things look black. All right, so just be mindful of that. Then the next thing they can ask you about is filters. Okay, so filters, what's a filter do? It will absorb everything and will only allow that color to go through. Okay, so here in this spotlight, you've got all the colors of the rainbow, RGB, and what's come out here is only red. Okay, but this is a blue ball. So what does a blue ball do? It absorbs all the colors of the spectrum and only gives blue, but there's no blue coming to it, so it's not reflecting any blue. And that's your answer here. Okay, and this was, I think, it's about a 3-4 marker. So you have to literally everything I've just said there, put it into step by step. So spotlight emits all colors. In fact, just put down Roy G. Biv. Okay, you could put all colors of the spectrum, but I'm going to put that down. The red filter only allows red through. So then the red is absorbed by blue object, and that's what appears black. And then if you want an explanation of that, a blue object absorbs all colors and only emits blue, but there's no blue. Okay, that's why they've already told you it turns black. If the question was what color would the blue object look, you would say black. Now let's just give you if it was a blue filter, it would only allow blue through, and the blue object will reflect the blue, so the blue objects would look blue. Okay, if it was RGB, so if it was a green filter, the blue object would look black because the only thing hitting it is green. Therefore, it will absorb the green, and there's nothing to give out. There's no blue to give out. Okay, so let's just practice this a little bit. If I can take, let me think. If I take this picture, okay, and I put it here, and what we're going to do, if this works, right? So what we're going to do, let's take it a step further. So what if I said to you, it's not a red filter, but it's a magenta filter? Okay, magenta. No, magenta. You must know your secondary colors because this hasn't come up for a very, very long time. Okay, if it was a magenta filter, what would be allowed through? Okay, so if it's a magenta filter, what would be allowed through is red and blue. Okay, and if red and blue is passed through, the blue object will absorb the red and it would appear blue. Okay, does that make sense? Hopefully that makes sense. All right, because now two colors are hitting that blue ball. Okay, and one of them is the one that it wants to reflect. Now let's do another one, just see if you've really understood it. What if I had, let's say, a yellow filter? So ask yourself what would happen. So pause the video. If it's a yellow filter, what two colors would come through? Oh, sorry, let's put down, you're going to get Roy GB. Always state all the obvious stuff. So what two colors are going to come through? You're going to get red and green. So what would the blue ball look like? It would look black because it'll absorb both of them. There's no blue to reflect. And then if you had a, let's say you had a cyan filter, cyan, whoever you want to spell it. Again, all the colors of the spectrum are given out by the spotlight. The cyan filter absorbs most of them, or rather will only allow this time blue and green. So what color would the blue ball look like? Blue, because blue is there, so it appears blue. Okay, so that's just some basics of filters. All right, so let's just do another one. I should have hopefully you made notes on that. What if I said to you, you had a red filter and you had a ball? The ball is not a blue object. It's a red and blue striped ball. What would happen here? So the red filter only allows red through because all the colors of the spectrum are given by the spotlight, and therefore the red stripe would look red, the blue stripe would look black. Okay, hopefully that makes sense. Okay, so let's just do another one just to make sure you've understood it. Again, pause it before you go through the answer. What's going on? Can I delete? Try again. Right, there you go. Right, so let's do another one. So let's say, for example, you've got a cyan filter and you've got a, this time, you've got three colors on there. So let's say you've got a blue / red / green striped ball. Okay, so what do you know? You've got all the colors of the spectrum coming out from the spotlight because it's white light. Here, cyan would only let through blue and green. So the blue would look blue. The blue part of the ball would look blue. The red part of the ball would look, there's no red coming through. So that would look black. And the green part of the ball would look green. Okay, so this is key. Make sure you memorize it. Okay, if you memorize that, it gets easy. All right, hopefully that helps. There's half an hour on the predicts as well as the other two videos I sent out. Any questions, last minute emails or last minute questions as soon as you can, please. Okay, hopefully that helps them. Take it easy. Good luck with your test.